Well, this is a unorthodox way of teaching a lesson, but I had to be out today, which I told you guys about yesterday, and just want to make sure that we're moving along. We're going to be doing section 4.3 today. And in 4.3, we're going to be discovering something called the number e. And this following task that you see in the note-taking sheet that you grabbed on the way in, or that the sub has handed out, is going to be using a power of 10 that we're going to plug into this expression of 1 plus 1 over n to the n power. Now, this expression is one that was just something that a mathematician a long time ago, Leonhard Euler, was looking at what would happen if I were using this fraction in here, and this should remind you of the M&M lab and that whole idea of the rate right here. This looks like growth. And if I make a smaller and smaller fraction by making numbers for n getting bigger down here and raising it to that same power, what kind of thing am I going to see happen here? What kind of relationship with the numbers? And as we go through this, we're going to be plugging in different numbers in for n. Now you're going to plug it in for the denominator here and in the exponent up there as you're working through it. Now when we do this, we want to be using, instead of 10 to the first, use 10. 10 to the second, we use 100 when we're plugging in, and so forth. You don't want to actually use the exponents there, but we're plugging in powers of 10 and seeing what's going to happen in the numbers. And what you're going to do is you're going to calculate this out in your calculator and start getting these numbers right here. And what I want you to do in your group is discuss what relationship you're seeing. What's happening with the numbers as the number of that you're plugging in gets bigger? What's happening with the outputs? And you're going to notice something happen. We'll discuss that in a minute. So take a minute and calculate this table out and see what you get. If you're not sure what I mean, I can do this first one with base just 10 to the first, and then you can see how it works out. So if I plug in this, I have 1 plus 1 over 10, and then I raise it to the 10th power. I can type that in my calculator just the way I see it. 1 plus 1 divided by 10, raise it up with the up caret symbol to the 10th power. And let's round to the thousandths place. .594. And go ahead and continue filling in this table. You should be a step ahead of me or more as you're going through, and I'm just going to be putting in the numbers so that you can check your work. going to go one decimal further just to kind of see what's happening there. So in your groups right now, you should be discussing what's happening with the numbers as the number for n became larger. What you should have noticed was the number was increasing, and this discussion hopefully is happening, that the numbers were increasing each time. And they do continue to increase, but something seems to be happening. And you should have noticed that the increase was slowing down. And when this increase slows down, it seems to be approaching some consistent number. It started leveling off to this 2.7182. Now if you round it up, 2.7183. But this number is starting to level off and continually become this right here, which is what you just discovered is the number E. Now, like I said before, this guy's name was Leonard Euler, pronounced like the old Houston Oilers before they became the Houston Texans. This is way back in the 1700s. And notice he was a little bit vain, obviously. He named that after himself. He chose the letter of his last name as the number E after himself. The number E, if you notice, is this number that the decimal keeps going forever. And it's not in this particular pattern. It doesn't have repeating decimals or anything. And it just continues and continues. We call this an irrational number. It cannot be written as a fraction. Now there should be another type of number that you're thinking of that's similar to E, where it's a decimal that keeps going forever. We can't write it as a fraction, and it's a symbol, just like the E, that represents it. Hopefully we are all thinking of pi. So pi represents a number, 3.1416, ... and E is the same kind of an idea. What are we going to use E for? Well, we're in the exponential chapter, so if you notice up here in the definition, or the title of 4.3, the base is actually going to be used as an E. It's called the natural base, is what we call it, since it's being used as a base of an exponent. Now, what kind of problems are we going to be doing with base E? Well, what we're going to do is we're going to look at first that since we're using E as a base, then we can have E as a base in exponential simplifying problems like properties that we did with exponents. Now, I know there's some on this sheet, but we're not really going to use this sheet much more than just that investigation. I did put some examples on a separate note-taking sheet here. So what we're going to do is we're going to simplify expressions just like exponent property problems. Notice that when we use base E, the bases will match because it's always going to be base E, so we can use our properties. This is the product property of exponents where we can now add our exponents. If I wrote those in expanded form, that'd be 3 E's and 4 E's for a total of e to the 7th. So we add our exponents. The quotient property will also apply. The numbers out front, treat it like a fraction. 10 divided by 5 simplifies to 2 on top. And we subtract our exponents. Where are there more? There's more on top, and specifically one more. And unfortunately, that's not your bell. And what we have here is our final answer. There's nothing left on the bottom, and we're done. For this one, when we pass out our exponent of a 2 to each thing, we have 5 to the second power times e to the negative 6x. Unfortunately, what we have here is a situation where we cannot let someone in right now. She knows who she is, but I cannot let her in. Sorry. Middle of a video. Alright, so this is going to flip to the bottom, negative exponent. We have 25 on top still because 5 squared is 25. And on bottom, e to the positive 6x. Now this one's a little bit different than what we had before because we haven't had any exponents with variables in them where it's an expression like this. But remember, the same property applies where we have to add our exponents together because it's the product. When we go to add these together, you're going to notice that it is e, we can combine like terms. We can put the x's together and add those. So we have e to the 8x plus 2 negative 4 gives us negative 2. And we can combine like terms like that and write that as our answer. Alright, next. This one's interesting because when we do our quotient property and subtract these, they're not like terms. So when we go to do this, we put whatever's on top comes first, and we subtract whatever's on the bottom because it's subtraction for the quotient property. And so we're just subtracting those exponents and showing it as an expression being subtracted. Since they're not like terms, we can't combine them, but we can at least show it as subtraction to show the property. The next thing we're going to have to do with base E is evaluate. Since we know E represents a number, 2.718, which we were looking at earlier, we know that it is a base. We can raise it to any power, calculate it out, and actually find out what the decimal answer is. So when it says the word evaluate, that's when we're going to use our calculator and type it in. Whatever you see for the exponent is exactly what you're going to type into your calculator. Now, in your calculator, how to get there for E raised to a power, you're going to hit your second button, the yellow button, and then ln. Notice behind ln, you'll see e to the x. Now what's going to happen when you actually hit that is e with the caret symbol in, it's going to give you some empty parentheses there. All you have to do is type in whatever the exponent is, whether it's a negative number, a decimal, it can be anything, it can be pi. We just plug that in as the exponent and hit enter and evaluate it. Please take a moment, if you have your calculator, to test this out. Make sure you're getting the same answer. So, again, this is 2.718 raised to the third power, which if we round off, and on these ones, the directions will tell you what to round off to. I'm not sure off the top of my head what the directions say. Usually it's the thousands, 3 decimal places, or 2. We'll go 3, just in case. 20.8086. The next one is raised to a radical. Don't let that throw you off. You literally just type in exactly what you see as the exponent in the parentheses. So second ln and then do second x squared, which is your square root button, 5, close your parentheses, and hit enter. I'll give you a second to try that out. You should have gotten 9.356. Alright, so now the notes are, if you flip over your note-taking sheet that you grabbed on the way in or got from the sub that had the investigation of E on it. So we're going to go and flip that over to the back. We're just going to look at the top here today of this stuff up here. I want you to know, in a function that has base E, it's exponential. And if you were to graph it, we're not actually going to practice the graphs with base E, but if we were to graph them, they're going to look like exponential growth or exponential decay. But if the base is always base E, then how can we determine what really is the base? Because remember, before we were comparing, was the base less than 1 or greater than 1 to determine if it was growth or decay. We can't do that now. So what it has to do with is with the exponent. The exponent, the r, is basically going to be a coefficient of x, and it's going to have a number up in the exponent with it now. When that number is positive, so if r is positive, the coefficient of x, the number up in the exponent, it's going to be exponential growth. An example of that would be 2e to the 2x. Notice the 2 is a positive number in front of x, and so we would say that that's going to be exponential growth. The other situation, obviously, if we're talking about positive versus negative, is if r is negative. And when that happens, we would say it's exponential decay. So if we had an example where it was a negative exponent, we can have decimals for r, we can have different things up there for that coefficient of x, but as long as it's negative, we say it's decay. The other thing we're going to be looking at today is word problems that are going to be dealing with this growth, decay, and using base E as well. There will be a couple situations where we'll see that happen. So this was normally going to be a PowerPoint, but I printed it off for the purpose of the video. And what we have is we have situations where it's going to be like the M&M lab, where the growth model is y equals a times quantity 1 plus r to the t. Now when we go to do this, as was with the M&M lab, a is your initial amount. It's whatever you're starting with in the problem. R is still our rate of growth. And the rate is going to be written as a decimal. So if it gives it to you as a percent of growth, we need to change it to a decimal, and we do this by dividing the percent by 100. What that'll do is make it into decimal form. And notice instead of x like it was on the M&M lab, it's t for time, because we talked the other day about how it's as time passes, stuff grows. Okay, so this is a problem that we have here where there are computer viruses in the year 1996. Now, way back then was when the internet was just starting to get launched, just starting to get popular, and there weren't as many different types of computer viruses. In this case, it started at 2,573. During the next 7 years, the number of incidents of viruses and other security incidents went up by 92% each year. That's a huge jump. In our M&M lab, when we were doubling our pile in front of us, remember that was a 50% growth. Just giving a comparison. So what we're going to do is we're going to write an exponential growth model that is going to be comparing the number of incidents n over the course of t years. When you write a model, the only two things we need to plug in, kind of like the model we did on the M&M lab, is a and r, the only two things that we need to plug in here. We leave y and t the way they are so that we can use this model for any number of years that pass. So when I write my model, it's going to be the initial amount of viruses was 2,573. Our rate is the percent. So if you divide that by 100, 92% is 0.92. And we leave t the way it is. Now what we'll see is simplifying that base as one number for the base. So 1.92. You just add it to 1. And we have our model. Now what we need to do is use our model to then find out how many incidents there were in 2003. Now you have to do a little bit of thinking for this, because when you plug in the year here to figure out the incidents, we have to figure out how many years passed. So in 2003, from 1996, how many years passed? Well, you just kind of count up, so 97, 98, 99, so you get to 2003, and we're using 7 years that have passed. So in our calculator, we can kind of just type this in. Remember using your little caret up arrow for raising it to that power. So if we have 2573 times 1.92, and we can raise that to the 7th power. 247,484 0.72 incidents. Now, if we're talking about real life situations here, and we have to make sure we have a label, but we aren't really going to have a decimal of or a portion of an incident. If that's the case, we're not up to 485. That's not a full incident, so we would round down in this case and say 247,484 if we wanted to be completely accurate based on the actual situation. So you have to kind of ask yourself, does it make sense to have a decimal or not? Obviously, if it was like money or something, things like that, you could have decimals. Just kind of think through the problem. I know it says graph the model, but we would just be able to kind of type that into our y equals button, type that function in, but use x instead of t, and then actually see what the graph looks like. Now, the reason that the graph comes into play is, what if it wanted to predict how many years it would be? When would there be 1,000,000 incidents or something like that? And you want to know when it would hit 1,000,000. Then you would want to look at the graph, go up your y-axis, and figure out at 1,000,000, sorry about that, at 1,000,000 incidents, what year was it? For instance, you can kind of see what I mean by that. I'm not sure when this is going to focus. If I had, and that was a horrible corner plane, but I can barely see around this corner when I'm drawing it, but if we had like an exponential growth curve here, and the incidents are going way up, and let's say that right here was where there was 1,000,000 incidents on the y-axis, and we just follow it over here to where it hits the line, follow it down, and let's say that was like 10 years or something, or x was 10. That would tell us about 10 years later. So we can use the graph to kind of help us predict or know, how many years down the line would it get to a certain y value. That's why a graph is important. So here is your turn to try it out. In your group, a diamond ring was purchased 20 years ago for $500. The value of the ring increased by 8% each year. You want to set up a growth model for the situation and use the model to find out what would the value of the ring be today. So maybe this ring was handed down to you. So, you had a loved one pass, and in the will, they're like, I want, this person to have this diamond ring. Now, they purchased it for $500. What's that value going to be? What is it going to be worth if you were to try to sell it now? Or maybe pay for college with it or whatever. Let's see how much money it would be over the course of 20 years. So go ahead and set up the growth model. Remember, the growth model does not have anything plugged in for Y or for T. You just have to plug in A and R. Then use the model for number 2. I'll give you a moment to calculate it out. Hopefully you chose 0.08 instead of 0.8. The most common mistake when there's just 1-digit percents is people just think they always have to just put it after the decimal, and that's incorrect. Remember, divide by 100 if you're not sure. 8 divided by 100 gives you 0.08. Now you should be using this model. If you added your base together and made it just one base, it would look like this. And 20 years later is what we're looking for, so T is 20. What you should have found was the amount at the end of the 20 years was now at $2,330. And this time the decimals do make sense. We're talking about money here. And we want to round to the hundredths place, so 48 cents. And there we are. And that's our growth model. Now we have a decay model. So similar idea, but remember in the M&M lab the only difference was we subtract the rate because it's going to be less than 1 for our base. It's going to be making something shrink. Now anytime you buy something new, unfortunately the value decreases over time now instead of the value going up. If you were to buy a new snowmobile that cost $4,200, and if anybody's really into this, they would know that this must have been years and years ago for a snowmobile to be brand new for only $4,200. But in this story it is. The value of the snowmobile decreases by 10% each year. We want to write the model for any number of years, then use it to estimate after 3 years. So my model would be, the initial value is what it starts at, 4,200. Over time, we're going to subtract that growth rate, and this time if we divide by 100, it's 0.10. It's the number of years T. Now if I use my model, after 3 years is what it wants to know. How much does it go down by? Again, you could have used a base as 0.9 if you subtracted that. That'd be fine. And we raise it to the third power for 3 years. And it's dropped to $30,061.80, which is unfortunate if you decided you wanted to resell that snowmobile. Now this is a graph that's set up, same idea as what I was talking about before, where we're going to use this graph to estimate the value. When would the snowmobile be worth $2,500? So what we do is we go to 2,500 on our y-axis. So if we were to graph this in our calculator and type in our function that we just did up here, and we look at 2,500 and follow it over, we could also go in our table of values and look for 2,500 in the table. and then we see where it hits the line, and we follow it straight down, and notice it is at 5 years. So in about 5 years is when we could expect it to be only worth $2,500. Okay, last you try, and then we'll be done for today. If you buy a brand new Chevy Bumblebee, now this is from the Transformers movies, and I know for it's been kind of a while. There's what like 4 or 5 of them already, but back then they actually came out with this release. Chevy actually released the Bumblebee car from the movie, and that you could buy and stuff. And I know this is probably a pretty inexpensive price for that, but if you had it all decked out and it ran you $19,500, and you got a really good deal, when you ride that right off the lot, you're going to lose the value. It's going to happen fast. No matter how much you keep it nice, you wax it, and you just wash it by hand daily, keep the inside all detailed, there's no stopping this exponential decay of your car's value. So if it depreciates in value at a rate of 12% each year, in 5 years when you were in college, how much will your Bumblebee Transformer ride be worth? Please take some time, set up your model, plug in how many years it's going to be, calculate it out, and see what you get. So your model should have looked like this when you set it up. So you might still be working, that's fine, but I just want to show you. Initial amount A goes out front. That was what the value started at when you bought it. We subtract our rate of decay. If you divide 12 by 100, we get that. And I'm going to go ahead and just plug the years in now because it didn't ask me for a model. It just wanted to know the money and wanted just to know that as the answer. And if you calculate that out, you'll find out how much it was worth after 5 years when you're in college. What could you sell it for at that point if you wanted to try to get your money back, or if you're just curious what it's worth? And you should have had an answer of $10,290.77. That's really depressing, isn't it? Only in 5 years, it's pretty much cut in half. The value went from around $20,000 down to $10,000. That's a pretty big cut, especially when you kept it nice and in mint condition. Doesn't even matter what miles you rode on it if it's decreasing at that exponential decay rate. I look forward to seeing you guys tomorrow, Friday, last day before vacation, and we'll keep getting to enjoy more of this exponential chapter. The sub does have the homework assignment, so he or she's going to post that for you guys so that you'll know what problems to do. It is going to be out of the textbook. See you tomorrow.